What happens when two black holes collide? Does the universe explode like a bomb? Does light vanish forever? Here is the terrifying truth: you wouldn't see anything at all. No fire, no flash, no sound. And yet, the collision leaves a mark, not in the sky, but in the fabric of reality itself. For a fraction of a second, space and time stretch and squeeze like the universe taking a sharp breath. And in 2019, that breath reached Earth. We didn't capture an image, we captured a signal, a zero point 0.1 second whisper that carried an impossible number. So what exactly collided in the dark? And why were the numbers impossible? The answer arrived on May 21st, 2019. At 3:02 UTC, a gravitational wavefront swept through our planet. It passed through the entire Earth silently and without leaving a mark we could feel. It didn't trigger earthquakes or disturb the oceans. To the human senses, it was a ghost, completely imperceptible. But to the Laser Interferometer Gravitational Wave Observatory LIGO in the United States and the Virgo detector in Italy, it was a whisper loud enough to be undeniable. The event was catalogued as GW190521. To understand the magnitude of this discovery, you have to understand the absurdity of the measurement. The wave that passed through Earth distorted the fabric of our reality by a factor of strain known as 10 to the power of minus 21. That is a decimal point followed by 20 zeros and a 1. In practical terms, detecting this signal is equivalent to measuring the distance to our nearest star system, Alpha Centauri, over 4 light-years away, and determining that distance with a precision less than the width of a human hair. It is without exaggeration the most precise measurement human beings have ever made. But the signal itself was just the courier. The message it carried was even more staggering. The collision that launched this wave didn't happen recently. Based on the redshift of the signal Z, approximately 0.8, the event occurred approximately 7 billion years ago, back when the universe was roughly half its current age. For eons, this ripple of gravity has been traveling through the void stretching across the expanding cosmos. By the time it reached our detectors, the source was already unimaginably far carried, even farther by the expansion of the universe. The signal lasted only 1/10 of a second. A short, low-frequency chirp that ended as quickly as it began. But encoded in that fleeting moment was data that would challenge our understanding of stellar evolution. However, before we can decode the impossible numbers hidden in that signal, we must first establish the ground rules of the game. We need to identify exactly what we are dealing with. What is a black hole, really? And when you get too close to one, what kills you? First, the darkness or the gravity? To solve a cosmic cold case, we first have to understand the nature of the trap. There is a pervasive pop culture myth that black holes are cosmic vacuum cleaners, voracious monsters that actively suck matter into their maws. This is fundamentally incorrect. Black holes do not suck. In the eyes of physics, they are simply regions of space where gravity has become the dominant force. If you were to magically replace our sun with a black hole of the exact same mass, Earth wouldn't be sucked in. We would freeze to death, certainly, but our orbit wouldn't change by a single inch. We would continue to circle the darkness, just as we circled the light. A black hole is not an object in the traditional sense. It is a place. It is a region where enough mass has been packed into a sufficiently small radius that the escape velocity required to leave exceeds the speed of light c. Since nothing in the universe can travel faster than light, nothing can escape. The boundary of this region is the event horizon. It is not a physical surface you can touch. It is a shadow line in space. It marks the point of no return. Once you cross it, all paths forward, backward, left, right lead inevitably to the center, to the singularity. But here is where the physics gets counterintuitive. The danger of a black hole depends entirely on its size. And contrary to expectation, the smaller ones can be far more destructive at the edge. We classify these gravitational sources into two main categories: stellar mass black holes and supermassive black holes. Stellar black holes are the corpses of massive stars, weighing between 5 and roughly 100 times the mass of our sun. Physically, they are tiny. Some are only the size of a large city, perhaps 30 kilometers across. Supermassive black holes reside at the hearts of galaxies weighing millions or billions of solar masses. They are titans with event horizons that could swallow our entire solar system. If you were falling toward a supermassive black hole, the experience would be strangely peaceful. Because the mass is spread over a vast volume, the gravity at the event horizon is strong, but the difference in gravity across your body is small. You could drift across the point of no return without noticing anything dramatic at all. You would survive the crossing only to be crushed later at the center. A stellar black hole offers no such mercy. Because its mass is concentrated into a city-sized sphere, the gravitational gradient, or tidal force, is extreme. If you approach feet first, the gravity pulling your feet would be significantly stronger than the gravity pulling your head. Long before you reach the event horizon, this difference would overcome the molecular bonds holding your body together. Long before you reach the event horizon, the tidal gradient would overwhelm the structural integrity of your body, stretching it into a long, thinning stream of matter. Astrophysicists call this spaghettification. It is a structural failure of biological matter against the geometry of space. The two sources responsible for GW 190521 were not supermassive giants. They were stellar-class objects, but they were unusually heavy. And when two objects of this density spiral into one another, they don't just pull on each other, they ruin the space around them. Now that we have established the physical profile of the sources, we can reconstruct the event. To understand that 0.1 second signal, we have to see what light cannot tell us. To understand the signal GW 190521, we must leave the safety of the laboratory and enter the simulation. We need to go back 7 billion years to the moment the two horizons became one. Imagine you are an observer in a vessel engineered to survive extreme tidal forces hovering just outside the danger zone of this binary system. The first thing you would notice is that your eyes are lying to you. In front of you are two massive stellar black holes, circling one another in a frantic, decaying orbit. But you don't see two black spheres against a static star field. Instead, you see a funhouse mirror of reality. The immense gravity of the pair acts as a lens bending the light from the stars behind them. The background starlight warps into arcs and partial rings, the kind of lensing patterns that can form Einstein rings under the right alignment, haloing the darkness. The entire sky looks liquid, as if the universe were being viewed through the bottom of a glass. If these black holes have accretion disks, swirling platters of superheated gas, they wouldn't look like uniform glowing donuts. Due to a phenomenon called relativistic Doppler, beaming the side of the disk spinning towards you would be blindingly bright and shifted into the blue part of the spectrum. The side spinning away from you would be dim and red. It creates a terrifying asymmetrical visage, a glowing, lopsided eye staring back from the void. But the true violence isn't in the light. It's in the geometry. As the two black holes spiral closer, a phase known as the inspiral, they aren't just moving through space, they are dragging space along with them. This phenomenon is called frame dragging. Think of space not as an empty vacuum, but as a thick fluid like molasses. As these massive objects spin and orbit, they stir the molasses. If you were floating near them, you wouldn't just be pulled down. You would be twisted sideways, forced to rotate with the twisting fabric of space-time itself. As the orbit decays, the speed increases. The two black holes accelerate to a significant percentage of the speed of light. They are no longer two distinct objects. They are a blur of gravitational potential energy. And then it happens. In the final fraction of a second, the event horizons touch. If two stars collided, there would be a thermal explosion visible across the galaxy. But when black holes collide, there is no thermal flash. There is no fire. Instead, the energy is released into the texture of reality. In that 0.1 second window, the duration of the chirp we heard on Earth to the two black holes become one. The new, larger black hole is born distorted, vibrating violently as it settles into a stable, rotating form. This settling down phase is called the ring down. During this brief convulsion, an unimaginable amount of energy is ejected. In the case of GW 19052, roughly 8 solar masses of energy, were radiated away as gravitational waves, the mass energy equivalent of about 2.7 million Earths. This energy didn't radiate as heat. It radiated as a tsunami of distorted geometry rippling out into the cosmos at the speed of light. For you, the observer in the simulation, the event is silent. The sound of the collision is actually the rhythmic stretching and squeezing of the space you occupy. Your vessel and everything inside it would be stretched and squeezed by an amount too small to feel, but large enough for a detector to measure. Then, as quickly as it began, the violence ceases. The new black hole sits alone in the darkness, silent and invisible once more. The wave fronts race away, destined to travel for 7 billion years, until they wash over a small rocky planet in the Milky Way. The reconstruction ends. We return to the control room on Earth. The visualization fades, replaced by the raw data on the monitors. We have confirmed the mechanism of the merger. But as the astrophysicists began to parse the specific masses involved in this collision, the celebration turned into confusion. A number appeared on the screen that shouldn't have been there, causing every theoretical model in the room to crumble. 85. When the LIGO team parsed the data from GW190521, they determined the masses of the two original objects that collided. One was substantial, but expected about 66 times the mass of the Sun, but the other was an anomaly. The second source weighed approximately 85 solar masses. To a layperson, this is just a number. To an astrophysicist, it's a violation of expectation, a crack in the model. For decades, our models of stellar evolution have drawn a clear map of how stars die. When a massive star runs out of fuel, it collapses under its own weight. If the star is heavy enough, this collapse creates a black hole. We routinely detect black holes below about 50 solar masses. They are among the most common remnants of massive stars. We also see supermassive monsters, but in between, there is a desert. There is a range of mass roughly between 50 and 130 solar masses, where black holes are expected to be extremely rare because ordinary stellar collapse struggles to produce them. This is known as the pair-instability mass gap. To understand why this gap exists, we have to look at the balance fight happening inside every living star. A star is a battlefield between two opposing forces. On one side, you have gravity constantly trying to crush the star inward. On the other side, you have radiation pressure generated by the nuclear fusion in the core, pushing outward. For millions of years, these two forces are locked in a stalemate, keeping the star stable. However, in extremely massive stars, the core gets so hot, and the photons, meaning particles of light, become so energetic that something strange happens. According to Einstein's equation, E=mc² energy can be converted into matter. In these hyperenergetic cores, high-energy gamma-ray photons suddenly collide and transform into pairs of electrons and positrons, also called anti-electrons. This is catastrophic for the star. The photons were the soldiers holding back the crushing weight of gravity. When they spontaneously convert into particle pairs, they effectively desert their post. The outward pressure drops instantly. With the pressure support, weakened gravity takes over. The star collapses inward with terrifying speed. This rapid compression ignites the remaining oxygen in the core all at once. The result isn't a normal supernova that leaves a black hole behind. It is a pair-instability supernova, PISN, a thermonuclear explosion, so violent that it completely obliterates the star. It leaves nothing behind. No neutron star, no black hole. Just a rapidly expanding cloud of gas. This means that nature has effectively banned the production of black holes in this 50 to 130 solar mass range. A star that might have produced an 85 solar mass black hole will instead be completely disrupted. So when LIGO detected an 85 solar mass object involved in the collisions, the scientific community was faced with a dilemma. Either our understanding of nuclear physics was fundamentally broken, or the object we detected was not natural. If a star couldn't have given birth to this 85 solar mass object, then where did it come from? The answer forces us to rethink the family tree of black holes. Most black holes we observe are first generation. They are the direct descendants of a single dead star. But in the dense chaotic environments of the universe, such as globular clusters or the disks of active galaxies, black holes live in crowded neighborhoods. The leading theory for GW190521 is that the 85 solar mass object wasn't born from a single star. It was likely a second-generation black hole. It was a second-generation black hole. Imagine a previous era millions of years prior. Two smaller standard black holes, perhaps 40 and 45 solar masses, collided and merged. They created a new, larger black hole weighing 85 solar masses. Normally, this remnant might be kicked out of its cluster, but if the environment was dense enough, it stayed trapped in the gravity well. It lurked in the dark, waiting. Eventually, it captured another partner, the 66 solar mass black hole, and began the dance that LIGO eventually detected. This makes the 85 solar mass object a kind of cosmic rebuild assembled from the remnants of earlier mergers. This hierarchical merger theory explains the impossible number. It turns the anomaly into evidence. It suggests that the universe is building immense structures not just through stellar death, but through a continuous cycle of gravitational cannibalism. The result of this specific collision, the merger of the 66 and 85 solar mass objects, created a final remnant of 142 solar masses. This final number is arguably the most important of all. It is the first definitive detection of an intermediate mass black hole, IMBH, the long-sought missing link between the small black holes in our backyard and the supermassive giants anchoring the galaxies. If the 85 solar mass object was indeed a forbidden second-generation black hole, it validates a terrifyingly violent picture of cosmic evolution. But extraordinary claims require extraordinary evidence. To prove that such a subtle signal actually came from such a massive event across 7 billion years of noise, we need a machine that borders on the impossible. To capture a signal as faint and forbidden as the one from the 85 solar mass anomaly, we built the most sensitive ruler in history, the Laser Interferometer Gravitational Wave Observatory, LIGO. LIGO is not a telescope. It doesn't look at the sky. It feels the fabric of reality, trembling. The facility consists of two massive L-shaped detectors situated thousands of kilometers apart, one in Hanford, Washington, and the other in Livingston, Louisiana. Each arm of the L is a vacuum tube stretching 4 kilometers long. The operating principle is a masterpiece of forensic engineering called interferometry. Here is how it works. A high-power laser beam is split into two. Half the light travels down one arm and half travels down the other. At the ends of these tubes, the light bounces off ultra-pure, meticulously polished mirrors and returns to the source and returns to the source. The machine is calibrated so that when the two beams return, they align perfectly out of phase. The peaks of one light wave line up with the valleys of the other. They cancel each other out, a phenomenon known as destructive interference. Two identical light waves perfectly out of phase can cancel into darkness. As long as the two arms remain exactly the same length, the photodetector at the heart of the machine sees nothing but dark silence. But the Earth is a noisy planet. The ground beneath the detectors is constantly vibrating, from the crashing of ocean waves hundreds of miles away to the rumble of trucks on nearby highways to the thermal jitter of atoms in the mirrors themselves. To a machine trying to detect changes in distance smaller than a proton, the Earth screams. To silence this chaos, the mirrors are suspended on quadruple pendulums and isolated by active seismic damping systems that push back against the ground's movement. It is one of the most vibration-isolated measurement systems ever built, waiting for a signal from the cosmos. On May 21, 2019, that signal arrived. When the gravitational wave from the merger passed through the detector, it distorted the 4-kilometer arms. One arm stretched slightly, the other squeezed. The distance the laser had to travel changed. The two beams of light returned, but they were no longer perfectly out of phase. They didn't cancel each other out. A flicker of light escaped the darkness and hit the detector. This flicker was the raw data. But to separate the cosmic signal from random noise, including quantum fluctuations in the laser light, scientists use a technique called matched filtering. They compare the raw noise against hundreds of thousands of theoretical waveform templates generated by Einstein's equations. They were looking for a specific fingerprint, and they found it. The signal matched the prediction for a heavy precessing binary merger. The machine had acted as a decoder, translating the vibrations of spacetime into a digital truth. The data strongly suggested a black hole in the mass gap range and forced scientists to take the second-generation scenario seriously. But every action in physics has a reaction. When two monsters of this size merge, the new object they create doesn't just sit there, it suffers a violent consequence. The immediate result of the merger was the birth of a new entity, a single black hole weighing 142 solar masses. This object is one of the strongest pieces of evidence yet for an intermediate mass black hole, IMBH. It sits between two familiar populations, heavier than most stellar remnants we've observed, yet far lighter than the supermassive black holes that anchor galaxies. It is the missing link of cosmic evolution. But this newborn remnant likely did not remain where it formed. It was almost certainly exiled. When two black holes spiral together, they emit gravitational waves. If the two objects are identical same mass, no spin, these waves radiate symmetrically in all directions. But the GW190521 event was a mess of asymmetry. The masses were uneven, 85 versus 66, and their spins were likely misaligned. Because of this imbalance, the gravitational waves were emitted more strongly in one direction than the other. According to Newton's third law, every action has an equal and opposite reaction. As the waves carried momentum away in one direction, the newly formed black hole was kicked violently in the opposite direction. This phenomenon is called gravitational recoil, or simply the kick. The energy involved is staggering. Simulations show that under extreme conditions, a remnant black hole can be launched at speeds approaching 5,000 kilometers per second, that is over 11 million miles per hour. This is fast enough to escape many galaxies and even some massive ones under the right conditions. It means the 142 solar mass object may have been ejected from its parent star cluster immediately after birth. It is likely rocketing through the intergalactic void right now, a rogue black hole, invisible to telescopes, disconnected from any star system, drifting forever in the empty space between galaxies. It is a lonely fate for such a magnificent object. But its existence changes everything we thought we knew about how the universe grows. The detection of GW190521 did far more than just break a record. It filled a hole in the history of the universe. For decades, astronomers were puzzled by a gap in the cosmic census. We saw the stellar tombstones scattered through the galaxy, and we saw the supermassive monsters anchoring the centers of quasars. But we had no evidence of anything in between. There was no bridge connecting the small to the giants. The 142 solar mass remnant produced by this collision is that bridge. It shows that intermediate mass black holes are not just theoretical, they can form through mergers. It confirms that the universe builds its giants not just by feeding them gas, but through repeated mergers in a hierarchical chain. The forbidden 85 solar mass object was the first step. The 142 solar mass remnant is the next. Given enough time and enough mergers, these wandering ghosts could eventually become the seeds for the next generation of supermassive hearts. We are only just beginning to listen. GW190521 arrived at Earth after traveling for 7 billion years. It originated when the universe was half its current age. Today, due to the relentless expansion of space, the source region is effectively over 17 billion light-years away. The signal was faint, a mere whisper against the noise of our planet. But soon, we will stop relying on whispers. Future missions like the space-based detector LIGO and the underground Einstein telescope will open our ears to the entire cosmic symphony. We will hear these collisions not as rare anomalies, but as the constant rhythmic drumbeat of cosmic evolution. The universe is not a static, silent place. It is a dynamic arena where space is warped, time is twisted, and the impossible becomes reality in the dark. We used to think of black holes as the final end of the story. Now we know sometimes they are just the beginning.